So when we are discussing or solving problems involving continuous probability distributions, first thing that is very important to us is what is the PDF, right? What is the probability density function? That's the question is interested in. So that has to be given to us. Otherwise, we would not really know what the question want us to solve. Once we have PDF, we can do a lot of things. We can calculate the CDF, the cumulative distribution function. And the other two values that we are often interested in will be the expected value. Here, the expected value, we can think of it as the average, and the variance, written as var of x. So E of x and var of x. They are related, much like how we define them in the discrete probability distributions, except we don't use summation, we use integration. So integration is like the continuous form of summation, if you want to think about it that way. Now, how do we define it? Very simply, think of PDF like as if, I didn't say they are the same, but like as if it is a probability at the point X. Now, that doesn't really technically make sense. But if you think about it that way, this is exactly then the same form as discrete case, where we say expected value of X is sum of X times the probability at X. Yeah, so this is like exactly the same thing. X, the integration dummy variable, times PDF of X, how high it is at the point X. Then we we integrate over from the smallest X in the domain, in the sample space, to the largest X in the sample space. So we range across. Similarly, for variance of X, we can draw some similarities from the definition. It is the square of each value of X that is deviating from the mean of X. Remember, mean is like the pivot to balance the entire mountain, right? This distribution curve. So the deviation from the average, you square them, and then you times the height, which is how likely that value is, and then you integrate from smallest x to largest x. And that is exactly the kind of a similar definition as discrete case. And when we expand this out and simplify everything, it is possible to also show the expanded expanded form in the discrete case, where we have x squared times the probability of x at point x. Here we have PDF instead, right? Then we sum over it, and essentially that is the same. We integrate and find the expected value of x squared, isn't it? Look at this form, right? Instead of x, we say x squared. So one way to say it is this this term, the first term is actually e of x squared. Yeah, because then you will see how easy it is to just use the e notation. Expected value of x squared means instead of using little x, we use x squared, little x squared times PDF of x, and that's exactly replacing the first term, minus the square of the expected value. Yeah, so again, we have this very helpful sentence to help us remember this. The expected value of the square minus the square of the expected value is the variance, right? Of course, the expected value of x, right? But if we just drop the x, then it's very easy to remember that. Now remember, what is the status of x, the random variable x here? Is it a population or a sample? How come we never define var sample, the sample variance of x? Answer is not possible, right? Whether it is discrete distribution or continuous distribution, whenever we use the word distribution to associate with the random variable x, then x must be a population. It cannot be a sample. So here we can then use the expected notation. Okay, the E notation is not really defined for sample subset of a population. So we have to be very careful here. Nevertheless, when we deal with distributions, we need to worry more about getting the calculations right because it will always be population. It will never be a sample. Here's an example. Consider this very simple PDF, constant 1 over 6. Calculate the expected value and the variance. So we go through our basic definition. Expected value is integrate of just x times the PDF. No matter how complicated it is, we just stick an x outside and then we get this form. And we can, of course, move the constant term outside and integrate x. The integrated form of x is x squared over 2. So we have that. And then we make two copies, right? Half x squared minus half x squared. And then we plug in 6 into wherever x occurs in the first copy. We plug in 0. Where's my mouse? We plug in 0 into the second half x squared, wherever x occurs. And then straight away we get, what is it? So we move the half outside, we get 12. And the x squared, because x is 6, we get 36. So divide up, we get 3. But of course, we already know that, right? Because it's like having this rectangle here, and you ask, well, this is 0, this is 6. If you imagine this rectangle having some weight, like a brick, and you ask, where can I put a pivot so that the brick will balance? That means where's the center of gravity? And of course, almost without thinking, you will say it is at point 3 because if you put a pivot there, it will balance. In vacuum, maybe where there's no wind and no dust and all that. And that is exactly the right intuition, right? So you see that it is 3. The variance part is a little bit less easy to, fathom just by looking. So we need to go through the motion of all the calculations. So, well, it's not difficult, thankfully. It's just find the expected value of x squared. You can see this? Just stick on we paste onto it, x squared, and then next to the PDF, and then integrate over the whole range, 0 to 6. So once we do that, we integrate x squared because we move out the constant term. So x squared integrates to x cubed over 3. So same thing, make two copies, x cubed over 3 minus x cubed over 3. First copy, wherever x occurs, we put in a 6. Second copy, wherever x occurs, we put in a 0, which means the whole term is 0. And if you simplify everything, you should be able to get 3 again. Okay. Drop me a comment if you don't get 3, then we'll see what happens. But you can follow the mechanical process. The integration part actually is the least of the worry. In fact, it's the most mindless exercise. You just mechanically find the pattern and transform it using the integral table, and then do the copying and then substitution and then simplification. So it's the easiest part. Realizing that you have to calculate the variance, right? Because we're applying and we are wondering how risky this portfolio is, in our financial analysis. Realizing that, oh, that means I got to find the variance of this distribution. That is much more, how should I put it, value added, whether it's to yourself, to your customer, to your boss, to your organization. That realization to trigger, to initiate the use of this calculation is the value add. So be mindful of where your contribution is. All right. If you're stuck with the integration, don't blame yourself because this course is not about calculus. And if you're not good with calculus, we can always use packages, more advanced software and integral tables to help us find the value. Right. So it's the initiating the use of these expected value calculations and variance calculations.